For this video, I'll be going through general wave properties, success criteria C, define and use the term speed, frequency, wavelength, period, amplitude, including graphical representation. Okay, so for transverse wave, okay, I'll be focusing more on transverse wave for this success criteria. Transverse. Okay, we have two kinds of graph. The first graph is displacement distance graph, DD graph. Okay, so what does it show? It shows the displacement of particles in a transverse wave and how they change with their distance from the source of the wave. So the particle here is the furthest away from the source of vibration. Example. Okay, so we have two axes. The y-axis is displacement. That means how far the particle was moved. And the x-axis is distance, which shows the particle's position. Okay, there are a few terms that we need to memorize. What is the crest? The crest is the highest point in a wave. So A, B, and C, they are crests. Okay, if we have the highest position, we also have the lowest point, which is actually the trough. So example, X, Y, and Z, they are trough. Now, what is amplitude? Amplitude, you also need to memorize, is the maximum displacement of a wave particle from its rest position. So we see that for particle A, it was moved the most. Where is the rest position? The rest position is this line. Now, if there is no disturbance, all the particles should be on this level. But because it's a transverse wave, I shift the rope up and down, so the particles will be displaced. So particle A is displaced and it goes up. Okay, and it happens to go to the highest point. Okay, when it goes to the highest point, this vertical distance, it is the displacement. Okay, this is the maximum displacement, and therefore it will be the amplitude. So, example, if I have another particle here, okay, this is the rest position. It was only displaced this amount. So, that is not the maximum displacement. It is truly displaced, but it is not the maximum displacement. So, therefore, it is not the amplitude. So, in order to make something to make the wave bigger, have a larger amplitude, I need to use more energy to shift the rope up and down, isn't it? Okay, so we cover amplitude. You have learned that amplitude is a vector quantity. Vector quantity means there's direction. Okay, so the amplitude which is pointing upwards is taken as positive, whereas the one pointing downwards is negative. Therefore, this is also amplitude, but it's negative A. Okay, but the value should be the same if it is very balanced and nice transverse wave. Okay, so this is what I talked about just now. The amplitude of a wave determines the energy carried by the wave. Right, the greater the amplitude, the greater the energy the wave has. So far we have covered three terms: crest, trough, and amplitude. So make sure you memorize what is their definition. The next one is wavelength. It is the shortest distance between two wave particles which are in phase. Okay, in success criteria A, I said I will be going through what is in phase. Okay, so the meaning of in phase is that two particles are said to be in phase when they have the same displacement and are moving in the same direction with the same speed. So if I look at this wave, let me erase everything. If I look at this wave, A and B, they are in phase. Right? Let's look at what is in phase. Two particles are said to be in phase when they have the same displacement, right? A and B are both crests, so they have the same displacement. And are they moving in the same direction and the same speed? Now, at the highest point, what do you think the speed is? The speed is actually 0. Why is the velocity or speed 0 at this point? It's because they have already reached the highest point, right? Can you imagine if they continue to have some speed, wouldn't they move even higher? So if they are already at the highest point, their speed is 0, right? And they were both moving from the rest position all the way up to the highest position. So their direction of movement is the same. Okay, whereas for x and y, they are also in phase with one another. Similarly for z, right? And when they have reached the minimum position, their velocity is also 0, right? Because they have already reached the lowest point. So why wouldn't they shift even lower? Because their speed is 0. Okay, so why is this in phase important? Now, because of this definition, wavelength, and this is lambda, so it is written this way, lambda. It is the shortest distance, okay, between two wave particles which are in phase. Previously, we have talked about amplitude. Amplitude is actually talking about the vertical distance, which is actually the displacement. So for a DD graph, displacement distance graph, the displacement is the y-axis is for us to talk about the amplitude, to find out the amplitude. So since we have already used displacement, the y-axis, to look for the amplitude, now we focus on the x-axis, which is the horizontal distance, okay, which can actually tell us the wavelength. But how do we determine the wavelength? Now, two particles are said to be in phase when they have the same displacement and are moving in the same direction with the same speed. So we will need to look for those particles that are in phase, and they must be side by side to one another. Therefore, the wavelength for this wave is the horizontal distance between A and B. Similarly, if I have a very nice uniform wave, the horizontal distance between B and C is in phase. Okay? So, what is wavelength? This is the definition that you need to memorize. But there's also another definition. The wavelength of a transverse wave can also be defined as a distance between two successive crests or trough. Successive means side by side, one after another. So I look for the first crest, okay, and then I look for the next crest. The horizontal distance will then be the wavelength. Simple. And take note, SI unit of wavelength, because it's length, it is meters. So lambda, the SI unit for lambda is meters. And this is what I mentioned just now. The speed of the particle is 0 at the crest and trough, and maximum at the rest position. So this is something like your pendulum, isn't it? This is your pendulum. So at the highest position, right, the V is 0. Okay, because if we can link it to our gravitational potential energy or energy in the gravitational potential store, the GPE is max, but the KE is 0. Okay, but at the rest position, the GPE is actually 0 if this was taken as the reference position, right? But the KE is max because the V is max. So we use this knowledge for our wave here. This particle here is at the rest position. It actually has the maximum speed or maximum velocity. But later on, we'll need to find out what is the direction that is moving. Because if we talk about these two particles, okay, they are both at the same position, does that mean that this is the wavelength? It may not be. So later on, I need to teach you how to find the wavelength. If you are talking about positions in the rest position, particles in the rest position. Okay, so maybe I would also like to highlight this thing. Okay, besides using the crest and the trough, right, successive crest and trough, we can also use the idea that wavelength is the length that the wave complete or move. Okay, the distance that a complete wave move. So we need to find out how to determine a complete wave. When is a wave complete? So imagine if I were to start from here. So this is the rest position. So if I were to start tracing the wave this way, it will go to a maximum point. Then it will come back down, okay, and reach this rest position again. But has it completed one cycle? Not yet, right? So it will continue to move down. It will reach the minimum, and then it will go back to the original rest position. So when I trace this out, it is a complete wave. Okay, maybe I can use the pendulum to help me again. So imagine I have a pendulum. I release it. So currently it is at the maximum position. Let's call this position A. And it moves down to the rest position at B. Okay, then it should go up to this position C. Is this one complete oscillation? You have learned in the pendulum, to find the period of a pendulum, this is actually half a revolution. So in order to complete one revolution, it needs to go from A to B, and then to C, and then back to B, and back to A again. So this will be one complete oscillation. So if I were to take each arrow as a step, so there's step 1, step 2, step 3, step 4. So we need 4 steps to complete one oscillation. Similarly, I can apply this to my waves. So this is step 1, step 2, step 3, and step 4. Okay, so this is easy because you can see that the wave profile, it completes one wave. But what if I were to choose this position? Okay, so if I were to trace, and if I were to come to here, you will see that this is not actually one complete wave, right? It needs to go past the other maximum position, and then this will be 2 particles that are in phase, and this will be the wavelength. Okay, so that is for displacement distance graph. So what can we get from displacement distance graph? Let's call it DD graph. I can get from the y-axis, which is displacement. Okay, I can get the amplitude. From the x-axis, which is distance, I can get wavelength. Okay, so the wavelength will require you to either identify 2 successive crests or trough, or identify what is the horizontal distance that the wave makes, that a complete wave makes. That means you need to know the concept of a complete wave, and complete wave needs 4 steps. Please remember these 4 steps because later on we'll be using it. So the next graph that we have is a displacement time graph. So again, this is my y-axis. This is my y-axis, and my time will be the x-axis. So what can we actually get from this graph? So it shows us a transverse wave. Okay, it shows how the displacement of a particle. Just now, displacement distance is many particles, but within a certain time. Okay, so you can take a displacement distance graph to be like a photo. It shows all the particles at a certain time frame. Okay, so it's like a photo. Whereas for displacement time graph, as time goes by, I'm only showing the movement of this particle a very particular particle, okay, showing its motion. So it is like a video. Okay, but anyway, what can we get from displacement time graph? We have the same thing because we have displacement. So the vertical distance, the displacement, will actually be the amplitude. So we are settled with the y-axis. What can we get from the x-axis then? Because it is time, so can we apply what is a complete wave? So imagine I start from here, it goes, right? Not yet. This is a complete wave. One more example, if I were to start from here, B, this will show the profile of a complete wave. 1 step, 2 step, 3 step, 4 step. So we need 4 steps to make a wave. Okay, so this horizontal distance, but because it is now in terms of time, will then be the time taken to complete a wave, which will then be the definition, the period. It is the time taken by each point on a wave to complete one oscillation. Okay, so from our x-axis, we can actually get period. Now, what is period? In a wave term, it is the time taken by each point on a wave to complete one oscillation. So now you can actually determine what is the information that you can get from a DT graph. DT graph, same thing. Y-axis, it is displacement. We can get amplitude. X-axis, it is time. We can get period. And we use capital letter T to denote period. So next thing we can get is frequency. Now frequency, this is definition for period. Frequency is the number of vibrations a wave particle makes in 1 second. Okay, you need to memorize this. And we have a formula. Frequency is also the number of crests that go through a point per second. That means we have this formula, F equals to 1 over T. That means it's inverse. Okay, the longer the period, the smaller the frequency. Yeah. Okay, and the SI unit for frequency is this hertz. Capital H, small letter Z. Which means to say, if I have my period, okay, I inverse it, I can get my frequency. So this is roughly what we can get from a DD and a DT graph. Okay, but what can we do with frequency? What can we do with wavelength? What can we do with frequency? What can we do with period? Now let me write down the units. Wavelength, the SI unit is meter. Frequency, the SI unit is hertz. Period, the units is S. Correct? Seconds, SI unit. So imagine if I put my wavelength over T, which is as if I have the units of meters over second. And meter over second is meter per second, which is actually the unit for speed. That means V equals to lambda over T. And we have this new formula. Okay, so wave speed is the distance traveled by a wave per second. And if I know the wavelength, I know the period, right? Wavelength's unit is meters, period's unit is seconds. Meter over seconds, I can find the speed, meter per second. And because frequency is 1 over T, therefore I can have a single line formula, V equals to F lambda. And this is the ultimate aim. So if you look at O-level questions, sometimes they'll give you DD and DT graph. What's the purpose? DD graph will give you the wavelength. DT graph, they'll give you the period, which you can find the frequency. And then the last question they will ask you to find is to determine the wave speed. So if I know wavelength, I know period, I know frequency, I can then have this formula to find the wave speed. That is all. Okay, some note to some things to take note of. Displacement distance graph, DD graph, gives the amplitude and wavelength. You already know this. Displacement time graph gives the amplitude, right, and period. If they are the same wave, they should have the same amplitude. Okay. So displacement distance graph shows the displacement of all particles at a particular time instant, which is a photograph. Displacement time graph shows displacement of one particle for the whole time duration. So it's a video of one particle. So you are not required to know what the gradient of the graph represents. I know a lot of you are scared of finding gradient, but we don't need to know the gradient. Okay, so this is for success criteria C.